The scientific method. What is it? Hello and welcome to my channel. My name is Nuo Shen, and we will explore the nature of science, how it works, and the great powers of the scientific method. Let's start by saying what science is not. Science is neither fantasy nor science fiction, although I find it fascinating that many sci-fi predictions really happened in the real world. This is a great idea for yet another video, is it not? Okay, what is science? The word science comes from Latin scientia and means knowledge. The word knowledge comprehends a vast territory. Every branch of human culture is made of knowledge, even superstitions. And knowledge was transmitted orally, before the invention of writing, and then recorded by written symbols or characters for future generations. But knowledge can also deviate by reality. An astrologist talks nonsense about the future. He might have knowledge of the positions of planets and stars and derive some sort of obscure path for your career or the love of your life waiting behind the next corner. But that is not science, is it? We will see why soon enough, and there will be a video about why astrology is just a fake, nonsensical belief system that has no scientific foundation and persists only through cultural tradition and cognitive bias. Galileo Galilei is universally known as the father of science. In fact, he was one of the first modern thinkers to discover that the laws of nature are governed by mathematics, and he was the first man to design and set the rules of modern science and its methods. Strictly speaking, science is a systematic and logical approach to discovering how things in the universe work. As we will see in a few moments, it is not an easy path, often studded with failures and deceptions. But no important goal is achieved by walking on a bed of roses. Instead, it is the result of fatigue, dedication, perseverance, careful thinking, and very importantly, the ability to think outside the box. There was a time when the world was explored with the power of the mind only, often due to the lack of technological instruments. Democritus, a Greek philosopher from the 5th century BC, hypothesized that everything was made of atoms, the uncuttable, from the Greek atomos, the tiniest unit of matter. We now know that the atoms are real, and they are also quite cuttable, as the people from Hiroshima and Nagasaki unfortunately know all too well. But the point is that Democritus just thought about atoms, but he didn't have any chance to prove their existence. His ideas were born inside his mind, not by observation. However, the procedure with which we study the world does not depend on instruments. Of course, the deeper you go into the comprehension of the world, the more sophisticated instruments you need. For example, the discovery of gravitational waves could only be discovered with state-of-the-art technology, year 2018 AD. But besides the instruments, it is only a matter of the approach method, the systematic rules that allow you to give a substantial explanation to any physical event. The scientific method is quite an intellectual endeavor, and it is based on observation, logic, and skepticism. Skepticism? Yes, you have heard it correctly. Skepticism is the core part of a scientific approach. Every theory or rule discovered by science is true, until otherwise proven. And that's the power and difference of science from any other discipline. Faith and religion will tell you absolute truths, truths that will never be questioned. Conversely, science will never tell you that a fact is absolutely true, but will give you a reasonable amount of probability that a theory is correct, still until otherwise proven. Where does this probability come from? It comes from evidence and repetitive tests carried out by everyone in the scientific community, globally. Ancient roots. Science begins with curiosity. In ancient Greece, thinkers like Aristotle emphasized observation and classification of nature. His method was systematic, but often lacked experimentation. Euclid showed that from a few axioms, one could deduce entire structures of knowledge, inspiring a deductive spirit in science. During Hellenism, Eratosthenes of Cyrene worked out a brilliant method to calculate the circumference of the Earth, with just sticks, feet, and a remarkable mind. Yes, the ancient people knew the Earth was round, not flat. In the Islamic Golden Age between the 10th and 11th centuries, Ibn al-Haytham, also known as Al-Hazen, championed experiments, especially in optics, arguing that hypotheses must be tested by observation and repeatable methods. This was a crucial shift. It suggested that even great thinkers could be wrong, and that evidence, not authority, should decide. A great achievement. The 16th and 17th centuries transformed science. Francis Bacon proposed an inductive method. Knowledge should be built from systematic observation, stripped of bias. Galileo Galilei added mathematics and experiments. He rolled balls down inclined planes to explore gravity, measured motion. He understood, along with Kepler, that the Earth orbits around the Sun and demonstrated that nature could be described in quantitative laws, one of the greatest leaps forward in the history of mankind. Robert Boyle, a founder of modern chemistry, promoted the importance of repeatable experiments and careful record keeping. Isaac Newton then unified mathematics, invented, independently and at the same time as Gottfried Wilhelm Leibniz, calculus, a powerful tool to measure change. He combined observation and experiment in a revolutionary synthesis. His laws of motion and gravitation showed that the same principles apply both on Earth and in the heavens. With the Enlightenment and the 19th century, science grew into a collective enterprise. Laboratories spread, instruments became more precise, microscopes revealed cells, telescopes revealed galaxies, spectroscopes decoded chemical signatures. Statistics matured, allowing scientists to measure uncertainty. In medicine, controlled clinical trials emerged. In biology, Louis Pasteur used carefully designed experiments to disprove spontaneous generation. In the 20th century, two thinkers reframed the philosophy of science. Karl Popper insisted that scientific theories must be falsifiable, that is, open to tests that could prove them wrong. I cannot stress this enough. Theories must be falsifiable, open to tests that could prove them wrong. A theory that postulates the existence of universes forever causally disconnected from ours is not falsifiable because falsifiability requires testability. For a scientific theory to be falsifiable, it must make predictions that can, at least in principle, be compared with observations or experiments in our universe. Causal disconnection means no interaction. If another universe is defined as being completely causally disconnected, then no information, no particles, no radiation, and no influence of any kind can ever cross into our universe. No possible observation could refute it. Since nothing from those universes can reach us, we cannot design an experiment, collect data, or make an observation that would contradict their existence. It explains everything and excludes nothing. Whether we observe particular constants, galaxies, or particles, the theory would still be consistent because it does not constrain what must be observed in our universe. Another example can be a theory that postulates the existence of a big red dragon inside a black hole. Except for Hawking radiation, nothing escapes a black hole. No information is given back to our space-time, and therefore there is no way to prove or disprove this theory. The theory is not falsifiable, hence not scientifically valuable. Still in the 20th century, Thomas Kuhn showed that science proceeds not only through gradual accumulation, but also through paradigm shifts, when old frameworks collapse and new ones replace them, as happened with relativity and quantum mechanics. New proven and tested theories overlap with old ones, often enriching them and making them more universal. Einstein's theory of general relativity does not erase Newton's laws of gravitation. It enhances them. Newton's laws are still valid for non-relativistic systems. We landed on the moon with Newton's laws. But general relativity puts things in a more, in fact, general context, including relativistic systems, and an explanation of gravity as a warp in the space-time continuum that depends on the mass of an object. By the 20th century, science had matured into a professional, global practice, driven by universities, journals, and increasingly sophisticated experiments. The scientific method is not a strict linear path, but a cycle with several core elements. Science begins with observation and curiosity, noticing something puzzling or regular. We ask a question. Background research explores the possibilities that what we observe has already been explained or can be explained with previous theories. If there are no theories available, a hypothesis is formulated, not a guess, but a proposed explanation with testable consequences. Controlled experiments or natural observations test predictions. Results are weighed statistically, considering uncertainties. Communication of results triggers independent confirmation by peer reviews, strengthening findings. Over time, multiple lines of evidence form theories which explain and predict phenomena. Let's clarify here and avoid misconceptions. A law describes what happens. A theory explains why, in physical terms, it happens. Uncertainty is not weakness. Quantified uncertainty strengthens credibility. Objectivity is achieved through methods, not through personal neutrality. Science is self-correcting. Replication and critique refine knowledge. This method highlights something very important. At any time we do not get experimental confirmation of the theory, then the theory is wrong. No matter how nice the theory is, no matter who proposed it, no matter how elegant or fancy it may be, if it is not confirmed by experimental evidence, it's wrong. This is why there is no such thing as belief in science. We cannot say, I believe in gravity. To this date, for example, we are not so sure of what gravity is. Einstein's gravity, as I mentioned earlier, is not a force of nature, but a warp in space-time. We postulate the existence of a gravitational force that must be carried by a particle, the graviton, but we haven't found evidence of gravitons yet. Therefore, we cannot say they exist. We cannot say, I believe that gravity is a force. We can only formulate theories and test them in a lab, but belief does not belong in science. The scientific method is also a mindset for daily life. Frame questions clearly. Consider alternative explanations. Test fairly, avoiding confirmation bias. Quantify outcomes and uncertainty. Invite criticism and correction. In an age of misinformation, these habits are civic virtues: patience with evidence, humility in uncertainty, and courage to revise beliefs. The scientific method is more than a set of steps. It is a cultural achievement. It asks us to replace authority with evidence, dogma with testing, and certainty with measured doubt, with skepticism. At its core, the method will remain what it has always been, a disciplined way of asking, what would it take to prove me wrong? That question, humble yet bold, is the engine of discovery. And it is why science, though imperfect, remains humanity's most reliable path to knowledge, to explore the what. If we'd embrace this mindset, the world would be devoid of all fake information. The path to meaning starts with the scientific method. It is the first step for a deeper understanding of who we are and the world we live in. As I said in my previous video, spirituality must find its solid roots in science, because any belief that goes against science is just a delusion, in my humble opinion. Thanks for watching. See you in my next video.